here. Now, today we start with the evaluation. We have to write the convection equation, convection differential equations. We have to obtain this type of equation for a particular case, simplified case. So a flat plate, like the one sketched here. As usual, we consider that the x direction is parallel to the flat plate and y direction is normal to the plate. We assume that a fluid arrives on the plate, moving parallel to the plate. The undisturbed temperature is D infinite and the undisturbed velocity is U infinite. We know that on the plate I have the development of a velocity boundary layer. That means I have a zone near to the plate in which I have a velocity gradient, the velocity change inside the boundary layer. The assumptions that I have to consider are parallel flow over a flat plate. Two-dimensional flow, we consider only the analysis in the xy plane, and we consider a unitary dimension in the direction normal to my slide, to my plane. We consider laminar flow. At the end of this chapter, I will introduce to you some element about turbulent flow. In this case, we consider only laminar flow. Newtonian fluid. Now you know what means Newtonian fluid. The Newtonian fluid is a fluid for which the surface shear stress is proportional to the gradient of the u velocity component in the y direction, and also constant thermophysical properties. We want to evaluate the velocity field, that means the u and v component of the velocity in the direction x and y, depending on the variable x and y for x and y for v. Free equation we have to write. The first is the conservation of mass, that means the continuity equation. Then I have the conservation of momentum. The momentum equation actually is free, means a free equation because I have one equation for each direction. For us, in two-dimensional case, it means two direction, but in general, I have one momentum equation for each direction I'm considering. And then the conservation of energy. We start by the continuity equation. At the beginning, we consider this small volume, here sketched with a dashed line in the xy plane, with dimension very small, the x and the y. And we have to write in a different way the equation here written. The mass flow rate that enter inside my small volume minus the mass flow rate that exit is equal to the variation in time of the mass of my control volume. V means control volumes. Control volume. And now I want to express this equation in a different way by using the velocity. And the mass content is nothing else the density that multiply the volume. Okay, we consider the volume, the x, the y, because we know that I assume a unitary dimension in the direction normal to the plane. So it will be the x, the y by 1. So this one is the mass. Then I have the mass flow rate that enter inside my volume, and I have an inlet contribution for the coordinates x. An inlet contribution is the product between among rho, density, u component of the velocity, and the area normal to this direction, that is dy by 1. So in is this one because it's density, velocity, area. dy is the area, remembering that I consider 1 as thickness in the other direction. The same as inlet contribution for the other direction, for the direction y. Rho, v, that is the velocity, dx is the area normal to the motion of the fluid, dx by 1. If I have to consider the outlet element, the outlet contribution, I have to consider them at the outlet, so at the coordinates x plus the x and y plus the y. And I consider the usual formulation by considering the variable and the derivative of a variable in the same direction, I mean considering by the x. So for the outlet contribution of a mass flow rate in the direction x, I will have x rho u plus the derivative of rho u in the x dx. The same for the outlet in the y direction, absolutely the same. And I write here, okay, sorry, here I have then the y. So as for the inlet contribution, here on the sketch I have only density and velocity. I have then to multiply by the area. So for this one, that is the component in the direction x, I have to multiply by the y, that is the area normal to this arrow. And for the direction y, I have to multiply by the x, that is the area normal to the direction y. Okay, it's clear? And, Giorno, prego, prego.
I'm sorry, Professor. Could you please add that in? I mean the interior of the control volume. I can understand rho u dy plus rho v dx. Could you please explain it again? I'm sorry.
In mass flow rate, this one?
Yes, yes, Professor.
Okay, okay. You know that the mass flow rate is always evaluated in the simpler way, density that multiply velocity that multiply the area of the cross section that must be crossed by. If you have to evaluate the mass flow rate in a pipe, you multiply the density by the velocity by the cross section of a pipe. Okay, so.
Oh yes, yes, yes.
Okay, so for me now the rho is the density, u is the velocity, the y is the area, in the sense that, for example, considering the inlet in the x direction, which is the area normal to the direction of the flow, is the y by 1, because I have from the beginning I have to assume that in the direction z normal to the plane of my slide, I imagine to consider unitary dimension. It's more clear now, and for the other direction is similar. Okay?
Yes, Professor. Yes,
okay.
Thank you, I got it.
Nothing. And okay. And now I have to substitute here what I write here in the equation, the first equation, the conservation of mass, and I obtain what you can read here, because obviously I simplify this one with this one and this one with this one, and I obtain this equation. If I want to write the same for the three-dimensional case, including the w component, the velocity in the z direction, I have to simply add the derivative of rho v, rho w in the z. You can rearrange this equation because we want to write it in a more compact way and in a more in the best manner from a mathematical point of view. And if you do the derivative of rho and u, here in the derivative you have a product of rho and u. This derivative is equal to rho by the derivative of u in the x plus u of the derivative of rho in x. If I develop all the steps of the derivative, I obtain a formulation that allow me to recognize this expression. So I will find a derivative for rho. I will find all the elements of this expression that I can call substantial derivative, and I use the capital D to indicate it. So you can try, but it's very simple. You have to do the derivative, and you can recognize all the contribution here for the density. Okay, you will find derivative of rho in tau plus u derivative of rho in x plus v derivative of u of rho in y plus w derivative of rho in z. And you can simply write substantial derivative, so capital D rho, capital D tau. That means all the summation of all the contribution here written. Plus what? Plus something that comes from the come si dice in inglese? Scalar product between the vector nabla. Vector nabla is simply the derivative in x, second element derivative y, third element derivative in z. So I have this element that is the scalar product between the nabla operator and the velocity vector. Is nothing, I have nothing, from a physical point of view, nothing new, simply a different way to write this expression. But is a more, from the mathematical point of view, it's better. Okay, and if I assume a compressible fluid, I keep uncompressible fluid means constant rho. I can obtain finally this expression. I simplify the first part, and I obtain that for incompressible fluid, I keep only the second part of the yellow equation, and I obtain there the derivative of u in x plus the derivative of v in y equal to 0. And this is the continuity equation. It's okay? Bene.
Yes, Professor, it's clear.
Yes, Professor.
Okay. The momentum equation is the second equation that I want to obtain, and it's based on the Newton's second law of motion. That means I have to write finally this equation. The summation of all the external forces acting in a direction. So in this case, the forces that I have to consider are the external forces on my control volume. So the summation of all these forces is equal to the variation in time of the momentum content of my control volume plus the momentum content that flows inside that flows outside my control volume minus the momentum flow that enter in my control volume. Which is the problem? It is correctly write the forces, because the other terms are not so difficult to be written. Which are the forces, the external forces that I have to consider? We have mainly two types of forces: the body forces and the surface forces. The body forces, now I skip to the second slide. The body forces that we will call capital X and capital Y. Capital X for the X direction, capital Y for the Y direction, are the forces that are proportional to the mass content of my volume. An example for us is the buoyancy forces. So the buoyancy forces in gravitational field are body forces because they depend on the mass of the system. For the moment you can consider like this. Okay, body forces are forces proportional to the mass. Then I have the surface forces that mainly can be divided in pressure and viscous effect. Pressure acts normally to the surface compression effect. So if I go to the next slide, pressure is compression forces normal to the surfaces. So are all forces normal to the boundary of my domain, of my control volume, in compression direction. And then I have the shear stress. The shear stress is forces, I have viscous effect. Viscous effect are divided themselves into components. Normal stress, that are normal to the boundary of my domain, but are tension effect. So are in the direction opposite with respect to the pressure. And shear stress. Shear stress are parallel to the boundary of my control volume. Here, in this sketch, you can see all the viscous stresses. Viscous stresses depend on the velocity and the gradient of the velocity. So, if the fluid is motionless, I have no viscous stresses. If a fluid is motionless, I keep pressure, but I have no viscous stresses. So viscous stresses appear only if I have a motion in the fluid. And here in this sketch you have an example of all the component tau, shear stress, and sigma normal stress for the different surfaces in the different direction. And
is zero if velocity is zero or its gradient is zero? So it means that there is no acceleration, so
yes.
It's laminar flow. No?
Ma anche se la velocità è zero il shear stress. Quindi in generale se è fermo non c'è.
Sul gradiente la velocità c'è,
sì.
Ma il gradiente è zero significa
è come se si muovesse a stantuffo, sì, ok, però poi di fatto, ok, but in the boundary layer you have acceleration. In the zone far out of the boundary layer, it's correct. You have a laminar. If I have a laminar flow, I have like a still motion of a portion of fluid. But in the boundary layer that we are analyzing, you have always a gradient of a velocity. And okay, the first subscript y identify the normal direction to the surface that I'm considering. So for example, look at this arrow, tau yx. Y means that this shear stress is applied to a surface that has y as normal direction, and this shear stress acts along x direction, that is the second subscript. For sigma yy means that refer to a surface with y normal in the direction y. So sigma, the normal shear stress, has the same subscript, the same letter as subscript, the shear stress two different letters, is not English. Come si dice lettera in inglese? Different character to identify the direction of normal to the surface and the direction itself of the shear stress. Okay. As usual, also in this case, for the coordinates x and the coordinate y, I consider tau yx, sigma yy, sigma xx, and tau xy. For the coordinates x plus dx, I have to do the first derivative. I have to add the first derivative of tau, for example, xy, in dx. The same for the normal stress. This case is for the x direction. I add the derivative in y, dy for the y direction. This is the list of external forces. So body forces and surface forces. The surface forces I divided in pressure and viscous effect. the viscous effect are divided in normal stress and shear stress. Now I want to write finally the external forces for the x direction. Here a sketch in which I have only the shear stress, the normal stress and the pressure for the x direction. So I have a pressure P that goes towards my volume from left to right at the coordinates x, and then I have a P component from right to left at the coordinate x plus dx, that is this one, P plus derivative of P in dx. Then, for normal stress, I have opposite direction with respect to the pressure for the coordinate x plus, for the coordinate x. For the coordinate x plus dx, I have to add the derivative in x. For the surface, for the shear stress, I have the same, is y, because the normal direction is y in the direction x, and for the coordinates y plus dy, I have to consider also the derivative in y dy. I write here, wait a moment, no. I consider all the contribution. I simplify what I want to, what I can simplify, and I write here in the x direction all the external forces. In a similar way, I can write the equations, the component for the y direction. So the external forces for the y direction are written here.
Sorry, Professor, but about P plus around the P around the X, that's the X. I think that P is minus P because the direction is toward the minus X. Am I right?
It's minus here.
But in the picture is positive.
Because they are
yes,
row,
yes.
Because their row is in the other direction.
But it's toward the minus. X is the direction is toward minus.
In fact, when you write here, you keep minus.
Oh, okay.
Okay.
Thank you. Yes, yes. Thank
okay. And now I have to, okay, I go back to the equation that I have to obtain. I have to write the external forces and the external forces. It's okay. The outlet and the inlet rate of momentum flow in the control volume. And here is written like this. Inlet is this inlet, this one, and outlet is this one and this one. And this is for the x direction, and the rate of momentum is the product between the mass flow rate and the velocity. And the mass flow rate here is only, okay, pay attention because it's not really a mass flow rate. In the bracket you have mass flow rate, but we have to add the x. So as for the previous case, here the mass flow rate actually will be rho v dx, because dx is the area normal to that direction. So you obtain the rate of momentum flow as the mass flow rate, but multiply the velocity. I'm considering the x component, and so I consider as velocity u. So this is the mass flow rate, rho v dx u. For that case, for that surface that is the y, I have the mass flow rate that is rho u dy u. This for the inlet in the two directions. If I have to calculate the outlet, I take the same the outlet is for the coordinate x plus dx, so I take the inlet and I add the derivative of the inlet in dx. Remember that everything is multiplied by dy due to the fact that the area is dy. For the other direction, absolutely the same. I have to take the inlet contribution plus its derivative in the y direction, dy. In this case, everything must be multiplied by dx, that is the area normal to the direction of the mass flow rate. Okay? In this equation, in this writing here, I have already considered outlet minus inlet. That was what I wanted here, outlet minus inlet for the x direction only. So this one minus this one, and this one minus this one. So here the difference is delta x, delta y, delta x, delta y, because you have to multiply this one by delta y and this one by delta x. It's clear for all of you? Vabbè. And finally, the last part of the equation is the momentum content of the control volume that I have to estimate as a variation in time. And the momentum content is the mass obtained as the density by the volume by the velocity. Mass multiplying the velocity, u, because I'm considering the x direction, and I consider the u velocity component. If I have to do the derivative in time, I simply do the derivative in time, nothing else. The x, the y are constant, and I keep the rho u in the tau. And so I combine together all the expression and I write the momentum equation for the direction x. Here I have the body force, the surface forces, the body forces, the variation content in time, the variation momentum content in time, and the outlet minus inlet flow of momentum. Similarly for the direction y. Okay. Now, if I, as for the previous case, I can do the calculation. I can do the derivative. Here, for example, I can split this derivative in rho by the derivative of u plus u by the derivative of rho, and so on for the other two derivatives. After doing this calculation, these calculations, I can recognize in some element of the second term, of the second member of this equation, the continuity equation. Knowing that the continuity equation is equal to 0, I can simplify the term of the second member that are the continuity equation. Simplifying, I obtain what you can find here. So this one is obtained really from us, from the calculation. So you step by step you are able to obtain this set of two equations, one for x direction and one for the y direction. From this moment now, I present to you different formulation for the Navier-Stokes equation, but not presenting all the mathematical steps. So up to this point, you are, I present to you all the passages, logical and physical and mathematical passages. From this point, trust me that the results are true. Newtonian fluid. Okay, we arrive here and we want to apply and to write the two equations here, the momentum equation, for the particular case of a Newtonian fluid. And I write here the definition of a Newtonian fluid. Now someone can say to me, okay, but you said that the Newtonian fluid was the fluid for which the first stress was only this part, not the bracket that you write now. You are true, but the complete definition of the Newtonian fluid is this one. The Newtonian fluids are the fluids for which the viscous effects can be written in this way: normal component and stress component. In the next lesson, we will apply the so-called boundary layer approximation. That are here. I go now a bit, okay. Boundary layer approximation are some approximation based on physical element, so it's not a creation without sense, but are based on physical observation of the phenomenon. And the boundary layer approximations allow us to simplify greatly the equation continuity, momentum, and energy. By means of the boundary layer approximation, we can find finally formulation for the continuity, its momentum, and energy equation more simple to be used and to be solved. Why I present to you this boundary layer approximation? The boundary layer approximation say to us that the gradient of a velocity are not equal, but the main one, the not relevant one, is only du in dy. So if I assume as true the boundary layer approximation, the only gradient that I have to keep is this one. And so also the shear stress remain like this one, me, du, and dy. So the basic definition written here for the Newtonian fluid, it's correct, but we consider nearly always the boundary layer approximation, for which I can neglect this second part in the bracket, and I can neglect the normal component because they are negligible. Ok? Le faccio ipnotizzate. Non so se state dormendo. Okay, some students here in classroom are sleeping. For the student at home, perhaps also the student at home in a more easy way, perhaps the student at home, but also in classroom the students are able to sleep here in a good way. Okay. I know that is okay. A transfer with this obviously this equation is not amazing. Okay, I can't do nothing different. Okay, so Newtonian.
This subject that and this material that you taught us, some of them are complicated, and because of this reason, some of us are sleeping, I think. But I don't know what's my problem, because I can't understand and I can't I'm a little confused because I can't calculate this equation or formula that you wrote. I'm sorry, but I don't know what should I do.
It's the problem of the basic knowledge that are requested for the master course. Okay, my final aim is not to be amazing, is to be clear. But I think that from the student is needed a basic level of knowledge from the mathematical point of view, and for the also thermodynamic and a bit of physics. I think that, okay, it's a lot of years that I teach this course, and typically student that has a sufficient basic knowledge at the end, okay, fine, perhaps something boring, sometimes boring the course, but they are able to understand everything. I can suggest, okay, if you need more explanation, you can write me an email and I add explanation, of course. But perhaps you need to recap something about mathematics, because I think that I explain step by step really everything. If you are not able to follow me, perhaps you have some not known about mathematics or something like that. So we can discuss about this point. You can write me an email if you want. So the importance for me is that for the main part of the students, I'm clear and you are able to follow me. Ragazzi in classe, you can follow me? Ok, va bene. So by using the Newtonian fluid viscous effect expression written here, inserting them in the previously obtained Navier-Stokes equation, I obtain the so-called Navier-Stokes equation. Introducing them in the previously momentum equation, I obtain the so-called Navier-Stokes equation. If I add another assumption, if I want to write the Navier-Stokes equation for fluid with uniform me is the dynamic viscosity, I obtain the following expression written here. The capital D is again the substantial derivative. So when I write capital D, I mean this one. This expression, that is the sum of different derivatives, one in time plus v that multiply the derivative in x plus v that multiply the derivative in y plus w that multiply the derivative in z. In this case, I have the substantial derivative of the u component of the velocity in time in the x direction equal to what? The minus the derivative of the gradient of the pressure in the x direction plus Laplace equation of u component of velocity again in the x direction plus the body forces in the x direction. We will obtain a different expression for the convection, for the forced convection and for the natural convection. This one is the general case for convection in general, including also the body forces. When we will analyze the case of forced convection, we will neglect the body forces. This one is for the general case. Similarly for the y direction. So for the momentum equation, I have actually two equations in the two-dimensional case, one for x and one for y. Here in yellow is the same, but written in a more compact way, substituting to the velocity for the x direction u and the velocity component v for the y direction, for example, the vector. So this yellow manner to write the equation include both the previous one, because I write the vector, I write the gradient. This notation means the gradient. If you go back, this one, okay, the gradient. So I have the derivative of p in x, here I have the derivative of p in y, here I have the gradient. That means one time the derivative in x, and for the other equation the derivative in y. Here again I have the vector instead of u and v, and the forces with the different components. That force, external forces, body forces as vector, including the different component x, y, capital X, capital Y, and eventually are also capital Z if I'm interested in the three-dimensional case. Other assumption, if I consider no viscous fluid for me equal to 0, I can simplify more the equation, obtaining the so-called Euler Equation that is written here. An important point is that if I solve together this equation yellow and the continuity equation that was here, I can find the velocity field. The solution of the two equations in yellow, the continuity equation and the momentum equation, allow to obtain the velocity field in the boundary layer. The final aim is to obtain the velocity field. The velocity field means what? The u and v component of the velocity in all the points of my boundary layer. When finally I obtain the vector v, that means the velocity field, I'm able to obtain also the shear stress. The shear stress in particular evaluated at the wall, that is tau s, surface shear stress. Tau s allows us to estimate also the pressure drop. For an engineer, after the equations, okay, this complicated derivatives, substantial derivative, which is the final aim, evaluate the transfer rate and the pressure drop. If I have to size some equipment, I have to know the transfer rate and the pressure drop associated to it. Knowing the velocity field, I can evaluate the surface shear stress and as a consequence the pressure drop. Okay, more or less, you have to, the manner to study, to follow the course is, I try to pay attention during the lesson. Then I go home, I read again the slides, I try to do the steps. If I'm not able, I ask to the professor by mail, by an appointment, and I repeat explanation. Not a problem, absolutely. Okay? Energy equation. The third equation that I have to write is the energy equation. So the energy balance for my control volume. The energy balance for my control volume is written according to this sketch, yes, here, where I write in the bracket the different contribution. On the first member, I have the rate of change of the energy content of the control volume in time. So, how much the energy content of the control volume change in time. Obviously, going back to the previously, obviously I have to assume that you are absolutely able to write an energy balance. That means you know, as your name, first, second law of thermodynamics. It's for this reason that a lot of students have the bridge career of applied physics, of applied thermodynamics, because for me, is the alphabet, okay? If you don't know the alphabet, you are not able to understand the language. If you don't know the first and second law of thermodynamics, it's impossible that you understand, okay? It's not, the course of energy engineering is not, have no interest in put some obstacle to the student. The bridge career is an help to you, okay? Think about it as the bridge career exams as an help to be able to follow in a properly way the courses of a master degree. Okay, rate of change of energy content of a control volume equal to what? Equal to the energy that enter minus the energy that exit, plus eventually the generation inside the volume minus the work. You know that when I write the energy balance, the first law of thermodynamics, I have to consider the heat, the flows in an open system in a control volume, and the work, minus the work done by the control volume on the ambient. We start by the first element, rate of change of energy content of the volume. E for me is the total energy for unit mass of a fluid. So this one is for unit mass. If I want to obtain the total energy, I have to multiply E, that is for unit mass, by the mass. The mass is density by volume. So the x, the y is again volume for us, because the system is again a small system in a two-dimensional domain, for which the third dimension is considered equal to 1. The third dimension in the direction normal to the plane xy is considered as 1. So for me, the x, the y is a volume. The x, the y bar rho is a mass, multiplied by the energy for unit mass, I have the energy. And I take the derivative in time because I want to obtain the energy content change in time of my control volume. Okay, net energy contribution by flowing stream in the control volume. That means the control volume means an open system. An open system means that I have a mass flow rate that can enter and a mass flow rate that can exit from my control volume. So the sketch is this one. I imagine to have an inlet mass flow rate and an outlet mass flow rate. The inlet are, this one is an inlet and this one is an inlet. Energy content associated to mass flow rate will be E, that is the energy for unit mass, multiplied by a mass flow rate. Mass flow rate is again the same as the previous case. Density that multiply velocity that multiply area. Mass flow rate is always like this. Density by velocity by area. So density is rho. Velocity x component is u. Area in the normal direction to u is the y. That is this one. The y by 1 in the normal direction to the plane. Inlet contribution in the x direction. Similarly, in the y direction, I have again rho v dx is the mass flow rate in that direction, but multiply E, that is the energy content for unit mass. Are you following me?
Yes, Professor.
Yes, Professor.
And the outlet contribution, as usual, I take the inlet and I do the derivative in the corresponding direction. Outlet in the x plus the x coordinates will be the derivative, the inlet plus the derivative in x by the x. I multiply everything by the y, that is the area. The same for the y direction. Groups writing everything in the x direction, I have this one. This one is the inlet, this one is the outlet, and finally obtain this one. In the y direction is the same, similarly. Then I have another contribution. Again, in the energy balance, I have a stream of mass flow rate that enter and a stream of mass flow rate that exit. Then that is a sort of convective contribution. Then I have to insert the conduction contribution. If my domain, if my control volume has a boundary that can receive by conduction heat or reject heat by conduction, I have to consider it. And again, my control volume here, and I have an inlet, it flux Q in the x direction, so Qx, x means in the x direction, dot means for unit time, so is a watt. 2 apexes means for unit area, so this one is watt divided square meter by the area. The area is always there, the y by 1 for this one for the x direction. For the y direction, similarly, q dot y, 2 apexes, it flux by the x, that is the area, the x by 1. For the outlet, it's the same. Again, I do the first, I take the inlet, I do the derivative in y if I'm considering the coordinates y plus the y by the y, and I multiply everything by the x to consider the area. For y, for x is the same. But I want to, okay, the Q dot two apexes say nothing to me. I want to use something that an engineer can understand better, that is temperature. So I use the Fourier Law. I'm speaking about conduction. I substitute this flux expression with the Fourier Law. So I have minus this, for example, Qx dot two apexes is minus K thermal conductivity, the T in the X, the Y. The Y is again this area, this one. And again, in the bracket here, in this bracket, instead of Q dot I have the Fourier Law. I have again minus K derivative of T in the X. I do all the calculation, I simplify where I can simplify, and finally for the X direction, I obtain this one, and I obtain this one for the Y direction. Okay? Ci siete? Then I have this part, we have obtained this one, this one, this one. We have to explain this one, the energy internal generation in the control volume and the work done by the control volume to the ambient. We start from this one, and internal generation, okay. If I imagine the general case for which, for example, I consider an electrical cable inside which I have, not an electrical cable, a nuclear reaction, because it's a solid electrical cable. A fuel with a chemical reaction inside, something that generates heat inside it, I can imagine to have also an heat generation. Heat generated is, this E gen is, as usual, watt divided cubic meter. I have to multiply by the volume, that is the X, the Y by 1. Okay? The last one is the work done by my control volume towards the exterior. How to calculate, how to evaluate it? I have to do the product between the force and the velocity. So in the X direction, the velocity is U, in the Y direction, the velocity is V. But what about the force? The force is the previously estimated. This one for the Fx, this one for the Xy. But pay attention, because in the momentum equation, I have to consider here, in that manner to writing the equation, the external forces acting on my control volume. In the energy equation, if I want to write on the second member this work done, are the work done by the control volume on the ambient. So the forces can be taken from this and from this, but with minus. So for example, Fx will be the P in the X, the X, the Y, minus the rho, the X, the Y, minus the tau, the Y, the X, the Y, minus capital X. In fact, here you find the forces obtained in the momentum equation with minus multiplied by U in the X direction and by V in the Y direction. I put together what I write up to this moment. Everything is multiplied by the X, the Y. So I eliminate everywhere the X, the Y. And obviously for the energy equation, I do not have, it's not a vector sort of vectorial formulation of the equation. I have one unique equation for the energy equation. So I put together X component and Y component, and I obtain this very long equation. Again, as for the momentum equation, up to this point, to the writing you find here, is exactly obtained step by step. Now I skip steps, and I present to you how finally we obtain as formulation for the energy forces to be used. But the idea is up to this point is followed step by step to give you an idea of the different components in an energy balance and how to write them step by step. And the work done by a body force, you remember that the body forces are the forces proportional to the mass content of my control volume. So typically are gravitational, electric, and magnetic effects. For us, typically gravitational effect. The body forces for us will be more or less only the buoyancy forces. The effect of the temperature field on the different density that create in gravitational field the buoyancy forces. Then here I skip a lot of steps, but you find the energy content E. If you neglect, and for example, this point is clear only if you know that the energy content can be split in internal energy plus gravitational energy plus potential energy. If you take into account only the internal energy, neglecting kinetic and potential energy variation, and you put together the internal energy and the pressure effect, defining the enthalpy function that is well known if you know all about the thermodynamics, you can rewrite the previous equation, this one, in a more compact way. So here in this slide, I present all the assumptions needed to finally obtain the final expression. Enthalpy, we have to introduce enthalpy. We have to introduce a function that express altogether that are able to express the viscous effect. And we define the viscous dissipation function written in this way, in this complex way, that group together the viscous effect. Frequently, this term, viscous dissipation function, is finally neglected in a lot of cases. Is relevant only with high-speed flow. For normal flow, can be neglected. With this list of assumptions, and the equation is simplified like this one. So this equation is nothing else. This one, by introducing the enthalpy, by introducing the viscous dissipation function, and rearranging the equation in this way. For in particular, other assumption for single phase substance, defining a beta, that is the volume expansion coefficient that you already know, because in the dimensional analysis we introduce beta, you can write the energy equation in another way. For ideal gases, other assumption, I know that is okay, I add assumption by assumption to simplify the equation. I obtain this expression, and finally, for incompressible fluid, I obtain the last equation in this slide. Now, a recap of the assumption that we have to consider. To obtain this yellow equation, that is the energy equation that we will use always in our course, I have to do this list of assumptions. K constant, thermal conductivity as a constant. No internal generation, because considering this equation, I have to neglect this one. I have to neglect also the viscous dissipation function. I have to neglect also this one. And I consider an incompressible fluid. With this list of assumptions added to the assumption that I made at the beginning. Obviously, the assumption at the beginning of this long chapter, of this long paragraph, are still valid. Parallel flow, two-dimensional flow, laminar flow, Newtonian fluid, constant property, plus the assumption added here at the end of this description of the energy equation allow us to obtain this yellow equation. That is the energy equation, also called Fourier equation for fluid. It's okay? And this is the last equation. This is the last slide for today, because if today I go on explaining also the boundary layer approximation, I think that you are not able to follow me.
Sorry, can you just come back?
Yes. But you can download the slide from the. Ah, ok, va bene. No, però puoi scaricarti.
No, l'ho scaricato già a casa, però.
Ok. No, vabbè, no problem. No, niente, dicevo solo che magari non lo sapevi. Uno scrive meglio sulle slide.
Can you please explain the dispersion equation again and why you should neglect it?
Okay, you neglect the internal generation. You neglect the particular case in which I have generation inside. I neglect the effect of a viscous dissipation function. That is this long expression that here I write that is relevant only for high-speed flow. So for us, frequently is negligible. And finally, incompressible fluid. With all this assumption, I can write the equation here. But finally, in the next slide, I recap all the assumptions that I have to consider to obtain this yellow set of equations that are our equation. The starting point for us now is this one is the continuity equation. Then I have two components of the momentum equation in the x direction and the y direction, and finally the energy equation. We obtained this list of equations assuming laminar flow, incompressible and Newtonian fluid, constant thermophysical property. We consider two-dimensional geometry. It's the same if you want to write a general case of three-dimensional geometry. You must add simply here a derivative of w in z, and you must add here a third momentum equation in the z direction that is absolutely similar to the other two. We consider negligible viscous effect and no internal generation. With this list of assumptions, we obtain this set of equations that are the equations for my boundary layer. I anticipate something about the next lesson. This is the starting point now. We want to simplify the equation obtained by applying the boundary layer approximation. So next week I will present to you which are the approximation for the boundary layer and which are the final formulation. The boundary layer approximation allows us to simplify something, and we will obtain another set of equations more simple that are listed here. Then we will do dimensions and formulation and so on. This central part of the course is without exercises because, okay, I have to do a part of the theory to arrive at a point in which I can do exercises. So for 2 weeks, no exercises is more complicated also to follow, but it's not possible to do in a different way. Okay, if you do not have any question, I stop now and see you in next Monday. It's okay for all of you?
Yes, Professor.
Okay. Okay.
Yes, Professor.
Okay, have a nice evening. Students, for everything, I'm here for you also as Deputy Coordinator of Energy Engineering. If you need explanation about something, write me an email and we meet by Teams also. Okay? Bye-bye.
Okay,
Thank you,
Professor.
bye.
Thank you. Bye-bye.
Questo